Hello. I would like to thank Vanessa for having us here this weekend. And it's only because of her I'm able to stand in front of you and speak. And it's been a pleasure meeting some of you and chatting with you and hearing about the well-being of your children. And it's a completely new experience for me as an analytical biochemist. So today I'll speak about the potentials of substrate replacement therapy for CDG type 1A. Oh. And here's the agenda. So since we are relatively new to the CDG community, I will talk a little bit about the company, Glycomine. Then I'll talk about the disease. And why we think substrate replacement therapy could work and how we are planning on making it work, supported by preliminary data, which is not perfect or complete, however, it has great potentials. I'll finish up by talking where we want to be with this development in the next 6 months. So Glycomine is a startup company based in San Francisco, California, and we are committed to helping patients that have no treatment options, and that's all of you in this room and more. Our goal is to develop therapeutics. It's to rapidly develop therapeutics for rare genetic disorders of protein glycosylation, of which there are about 100 of them. And most of them cause severe debilitation in patients and hardships on families. We are currently addressing 2 different CDGs, type 1A, as well as the NGY1 deficiency, together with the Grace Woolsey Foundation. So CDG1A is caused by the deficiency of the PMM2 enzyme, which is a cytosolic enzyme located within the fluid space of our cells. It mediates one of the very early steps in glycan biosynthesis, and its job is to convert mannose-6-phosphate to mannose-1-phosphate, which is then used to make GDP mannose, a nucleotide sugar, which is a key substrate and in glycan biosynthesis, as well as initiator of the synthesis of big sugar trees. And the big sugar trees are needed for proper end-linked protein glycosylation. So with disease, the PMM2 gene is defective, and that prohibits the PMM2 enzyme from making mannose-1-phosphate. Then there is an insufficient amount of GDP made that subsequently leads to loss of big sugar trees and results in protein hypoglycosylation. So in order to treat the root cause of the disease, one can replace the defective gene or the defective enzyme. However, it's quite difficult at the moment. So as an alternative, one can replace the missing substrate, and in this case, it's the mannose-1-phosphate that's missing. Sorry, didn't finish that. And these approaches have been tried before, and they have been proven to be successful with a few problems. So mannose-1-phosphate is a sugar, just like all glycans are sugars, and the sugar you use at home, they like to be dissolved in water. So meaning that they have hydrophilic, which is water-loving properties. Have you ever tried to dissolve sugar in butter, for example? When you make a cake, do you add the sugar to butter? Or probably not. You add it to the eggs, right? So that is why one of the reasons mannose-1-phosphate cannot enter the cells on its own, because the cell membranes are composed of fats. So in the past, what other scientists have done, they have chemically modified the mannose 1-phosphate that would allow its entry into the cell. However, the chemically modified substrate, when tested in patient cells, they turned out to be toxic, meaning that the cells died, so it's unsafe. Additional issues with the chemically modified mannose 1-phosphate was that the derivatives were chemically unstable and indicated the potential lack of absorption by the body, meaning that if injected into patients, the body would get rid of it within several minutes, and which is not enough time for absorption into the tissues that needed. So what do? We basically put mannose 1-phosphate in butter. And by butter, I mean lipids that we call liposomes. And we do it in a way where we make a ball of butter stuffed with mannose 1-phosphate. So what you're seeing here is a cross-section of the liposome containing the drug that's on the inside, and the lipids are on the outside. So the liposomes that we typically make are about 100 nanometers in size, and who knows what's a nanometer? Nanometer is actually really small. It's 1 times 10 to the negative 9 of a meter. So for example, a dust mite is about 200,000 nanometers. Human hair is about 80,000 nanometers. And so our liposomes that we make, the nanoparticles, the nanovehicles of the drug, are about the size of a flu virus. And they're about 70 times smaller than a red blood cell. So when injected into patients, the liposomes will be taken up by our cells via a very well-known mechanism called endocytosis. So once they are transported into the cell via organelles called endosomes, and the liposomes are designed in a way to escape the endosome and into the cytosol and release the drug where it's needed. So other great properties about liposomes are that they are biodegradable and non-immunogenic, meaning that they won't cause adverse reactions. They can be functionalized to target many different tissues, as well as the blood-brain barrier. They are very efficient carriers of small molecule drugs, stable and non-toxic. Additionally, they're FDA-approved drug and gene delivery vehicles. So there are several parameters I like to evaluate when developing or researching a therapy. And one of them is subcellular localization. So is the vehicle capable of taking the drug into a cell compartment where it's needed? So in our case, it's the cytosol. And safety of our patients is of enormous importance, and we want to evaluate drug toxicity as soon as possible, very early on in our research, because as you know, all drugs have adverse effects even if given at normal doses, but some can produce highly undesirable, dangerous, toxic effects. Third, we look at efficacy. So does the drug have the capacity to produce an effect? Does it have the ability to correct the deficiency? And in our case, does it have the ability to increase the levels of mannose 1-phosphate as well as GDP mannose and potentially correct abnormal glycosylation? And last, pharmacokinetics, which is defined as the movement of a drug into, through, and out of the body. How long does it take for it to get into the tissues? Which tissues does it get into, and how is it degraded, and how our body gets rid of it? So in order to be effective, mannose 1-phosphate needs to be delivered into the cytosol. which is the liquid space within the cell. So we have collected qualitative images of patient cells before and after treatment with the liposomal formulation of mannose-1 phosphate, and it's important to make sure that the drug stays in the cytosol and it doesn't end up in the lysosomes. And lysosomes are basically garbage disposals of our cells. In this experiment, we have stained certain organelles with fluorescent dyes where the nuclei were stained blue and the lysosomes, the garbage disposals, were stained green, whereas the drug was labeled with a red dye. So if the drug would be taken up by the garbage disposals or the lysosomes, we would expect the drug to show up in yellow. I don't know how well you can see the images. I can see them better on my computer. We would expect the drug to show up yellow because when you mix green and red, you end up with yellow. And what you can see from this photo is that most of the drug, I would say majority, all of the drug appears red. So these are very qualitative, so indicating that it didn't go into the lysosome for degradation, that it stayed within the lysosome, within the cytosol. So these are very qualitative experiments, but our next step is to really acquire more of quantitative data where we can fractionate the cells and make a lysosomal prep and cytosolic prep and measure the distribution between the different cellular compartments. So next, we looked if our therapeutic approach would be safe for our patients. So we treated fibroblasts with liposomal formulation of mannose-1 phosphate, as well as free mannose, which wasn't encapsulated in butter or the liposomes. So as you can see here, interestingly, what we observed was that mannose by itself, without the liposomal protection, when treated at high doses, ended up to be a little bit toxic, so our cell viability dropped to about 80%. And if you look at the trace for mannose-1 phosphate encapsulated into the liposome, we maintained our cell viability at both high concentrations of the lipid as well as the mannose-1 phosphate in it. So next, we looked if we can get any efficacy with our treatment. This experiment tells us whether this has potential or not based on the ability to restore missing mannose-1 phosphate as well as GDP mannose. So one thing I want to point out is unlike many academic labs, we are currently limited by the use of radioactive labeling or metabolic labeling in order to be able to trace what happens to the delivered mannose-1 phosphate. Is it incorporated into the glycans, the big sugar trees, and how is it processed? So we're in the process of developing alternative quantitative methods, labels, as well as drug treatment conditions to visualize the corrected LLO. However, we have been at the moment utilizing carbohydrate electrophoresis. We've been able to show that we have an increase in mannose-1 phosphate after treatment with the liposomal mannose-1 phosphate formulation, and the same was observed for GDP mannose. So next, we also wanted to evaluate look at the blood retention of our liposomal formulation of mannose-1 phosphate. So what we did is that we injected the drug we injected healthy mice with the drug and monitored its retention over time. And so we observed that with the current formulation that we are working with, the therapeutic is cleared after 18 hours. After 18 hours, the half of the therapeutic is cleared from the bloodstream. And after 48 hours, it basically drops to zero. This means that we have to optimize the formulation in order for it to be retained for much longer. And in the long run, this will actually reduce the frequencies of how often the patient is dosed with the therapeutic. So we are confident that can be easily done, and we are currently working on it. We also looked at the tissue distribution of the therapeutic because we want to be able to know which tissues are we going to be able to address. So the healthy mice was injected with the therapeutic, and the tissue that we looked at was fat tissue, heart, liver, kidney, and plasma. Or blood. And the time points we looked at was 1 hour, 6 hours, and 48 hours after injection. And what we observed was that the tissues that took up the smallest amount of the liposomal mannose 1-phosphate were fat, heart, and kidney. It was about 5% and less. And we don't know whether mannose 1-phosphate is needed in those tissues. Additionally, that's potentially a good thing because a lot of times drug-associated toxicity targets organs such as heart or kidney. So seeing that we don't have a lot of accumulation of our formulation there could be potentially a good thing. But what we saw was that majority of the drug was between plasma and the liver. So at time 1, we had about 70% in plasma and about 30% in the liver. And at time point 6 hours, the levels in plasma started dropping, but we saw a slight increase in the levels in the liver. And we didn't have any further the time points between 6 hours and 48 hours, which was our last, in order to minimize the number of animals in the study. So potentially there could be a higher liver uptake than 30%. But what does it mean? We believe that having the ability to deliver mannose 1-phosphate into the liver, we would be able to treat a lot of problems that the liver has. And as you know, majority of plasma glycoproteins are actually glycosylated, and they are produced in the liver. So we potentially would be able to restore the protein glycosylation of plasma proteins. And once this goes further, I would be very interested to see or compare the plasma glycoproteome globally instead of just focusing on transferrin, because potentially there are other proteins that we don't know of that are hypoglycosylated in blood that could be very important players for our organs to function properly. So we also attempted to measure the exogenous or delivered mannose 1-phosphate in blood and liver. However, we ran into some issues since blood and liver will have sugar 1-phosphates that are very similar to mannose 1-phosphate, similar in molecular weight, and with similar behavior with our methods that we use. So we need to develop better tools in order to be, and since we are limited by the fact that we can't use radioactivity, we have to develop better tools in order to be able to distinguish between the endogenous levels of mannose 1-phosphate or glucose 1-phosphate, galactose 1-phosphate, between what we can deliver. But that's in the works, and however, our initial data suggests that there was a significant increase in -1-phosphate in the liver. However, the blood levels stayed low, and we don't want -1-phosphate to be released in the bloodstream, otherwise it wouldn't be effective. We want the tissues to take it up. So we hope to report on this study in a few weeks. So this is just a summary of our findings and potential. So a liposomal formulation of -1-phosphate can deliver the missing substrate into the cytosol. It's non-toxic and at high concentrations of the lipid as well as -1-phosphate encapsulated in it. And it replaces the missing -1-phosphate, increases levels of GDP-mannose in vitro, and that tells us that it has a great potential to correct abnormal glycosylation. It is retained in blood for extended periods of time, which we are also working on improving. And it targets, as you saw, it targets several different tissues, but the delivery is lower. Its main target is actually liver, and if we can deliver there, we can also minimize some of the side effects. It's a targeted approach and with high retention in bloodstream. So we can potentially minimize some of the side effects of mannose treatment, for example, because it's given at such high concentrations. Here we wouldn't have to do it because it's much more specific or much more direct approach. What's next for us in the next 6 months? One, we need to improve the formulation in order to increase its half-life and retention in blood, and develop methods to demonstrate drug efficacy without the use of radioactive labels for both in vitro and in vivo testing. And we also would like to broaden the tissue distribution. I mean, we've only tested like 4 to 5 tissues, and we saw a little bit here and there, but majority was in the liver, which is a good thing. But we also want to be able to look at the possibility of delivery into the brain, and that can be done by modifications with ligands that can penetrate the blood-brain barrier. Alternatively, we can look at routes of administration other than IV. So here's our timeline for the next 6 months, and it's pretty aggressive, but we really want to be able to know whether it's a yes or no in the next 6 months. So we're addressing the blood retention issues right now, and we plan on repeating mice studies in December using a healthy mice, and it's going to be quite difficult to show efficacy in a healthy model, but there are definitely ways we can try. And in the early 2016, we want to know whether we have a clinically relevant therapeutic target. So here's our team. It's led by myself, and as I said before, I'm an analytical biochemist, and with experience in orphan drug development. I used to work on several enzyme replacement therapies at BioMarin, which is a major orphan drug developer in the Bay Area. And here we have Deidre Foley, and she's here today, and some of you probably met her. She's an outstanding scientist and geneticist and molecular and cell biologist. And we have Tape, who's an expert in, who's a biophysicist and expert in chemistry and drug delivery methods, and Sam, who's willing to repeat experiments over and over and again, which is quite important in what we're doing. And we are supported by our advisors, Tatiana, an expert in nanomedicine, and Dr. Entz, who's at Stanford Medicine, and he's really the local expert for CDG patients. And Matt Wilsey, he's the founder of the Grace Wilsey Foundation, and him and Matt might have created a world of resources and possibilities and experts to better understand NGLY1 as well as find treatments as soon as possible. So thank you, and we welcome you to visit us in San Francisco or our website, which should be live in a couple of months. Thank you.